Okay. So, this lecture is a continuation of module 3, and in module 3 we have learned how to do the reliability analysis of a distribution network. Okay. And in this particular lecture, that would be the last lecture, or I kept it as a part 2 of module 3. We will learn in this lecture some of the power quality problems or power quality issues of distribution networks. Okay. And a broad idea how to mitigate or how to characterize those power quality issues. Okay. So, this one lecture will only focus on a broad categorization and characterization, and also some mitigation approaches for various types of power quality issues which are encountered in power distribution networks. Okay. So, first of all let me give you a basic idea that what is power quality. Okay. What is the definition of power quality? Okay. So, as such there is no standardized definition, but in many books you will get different ways to define this term power quality. And in fact, this power quality is a such a big area nowadays that people do research, and it becomes a new paradigm of power system research. Okay. So, this is how this one of the books which I refer in the reference, that is authored by Professor Arindam Ghosh and led which they define this power quality. So, power quality is the ability of electrical grid or network to supply a clean and stable power to the customer. Again, there are two adjectives or terminologies, whatever you can call, that is clean and stable power. Again, the question is what is clean and what do you mean by stable power. Okay. So, in order to understand that, you have to know that what sort of disturbances, what sort of distortion or what sort of issues that we have in supplying a clean power. Okay. Now, electric power quality mainly involves this voltage and frequency and its waveform variation. Ideally, as a customer, that our goal or our need is to have a stable power supply, uninterruptible power supply, as well as that whatever supply that we are getting, that should have a proper magnitude, proper RMS values, that should have a proper frequency. And there is another thing that the waveform, voltage waveform that we are getting at our home, that should be a pure sinusoidal with a RMS value of the since we are a single phase customer. So, we wish to have 230 volt single phase 50 hertz a pure sinusoidal voltage source that we are intending to have from the utility. But due to various problems, no utilities in the world can ever give you the guarantee of having a pure sinusoidal voltage source, which is having exactly of your desired frequency. In India it is 50 hertz, and which is having the your RMS value as your desirable value, that is 230 volt. So, no utility can guarantee you. Okay. Now, then again coming back to the definition of this power quality, good power quality can be defined as steady supply voltage within the prescribed range of RMS value. So, although we intend as a single phase customers for single phase domestic customer, that we intend to have 230 volt RMS RMS source having a 50 hertz frequency and pure sinusoidal voltage, sinusoidal pure sinusoidal voltage. Okay. So, this is what our goal, this is our goal, or this is what we intend to have from electric utility, but as I said it will never get. So, we know that voltage will never be constant at 230 volt RMS value. So, we know that if it is within some range, let us say some 5% variation, then we can accept it. Okay. Similarly, in steady AC frequency, we will never get 50 hertz frequency constant throughout the day, throughout the month, throughout the year. Even it may so happen that in a particular day we will never get 50 hertz at any instant of time. So, we know that frequency will slightly vary, but we know that it should be as close to the rated value, and there is a band of variation of the frequency. If the frequency remains within the band, it is somewhat acceptable. Similarly, there is a specific band of this your RMS value of the supply voltage. If this voltage lies within this band, we can consider it as acceptable. Okay. Similarly, we are also concerned about this voltage waveform. So, we should we know that we intend to have a pure sinusoidal voltage source, but eventually we will not get it. Okay. So, this whatever the supply voltage we are getting, if you measure this voltage waveform and if you monitor it for some few hours, you will see it is far from the sinusoid. Okay. Although it is not exactly means pure sinusoidal, but we intend to have a as close as possible. And also if we have some distortion in the sinusoidal, how do you characterize those distortion, how do we quantify those distortion, those things we will study in this particular lecture. Okay. Now, as I said, there are various power quality problems, and first we need to understand what are those power quality problems. So, one is poor load power factor. This is one thing that many of you know. Second is harmonic contents in the load. What do you mean by harmonic contents? Harmonics I will discuss in one of my slides. Harmonics is basically generated because of distortion in your waveform of your supply voltage or load current, whichever we are getting or whichever is we are drawing. So, if they are pure sinusoid, there will be no harmonic contents, okay. But if they deviate from this pure sinusoid waveforms, then we will have some sort of harmonics into that. So, those things we will discuss. Similarly, waveform notching is another sort of waveform distortion we will discuss. Similarly, having DC component in the sinusoidal supply voltage is another power quality problem. Unbalance or imbalance of this supply voltage, which may be caused because of unbalancing of loads, or there are many other reasons. So, those things also we will discuss. Similarly, supply voltage waveform distortion, and some of the short duration and long duration voltage quality problems, and which we will discuss in this particular lecture. They are named as voltage sag, voltage swell, interruption, and so on. So, those things we will discuss, and finally, voltage flicker is another sort of voltage related disturbance, we will discuss that. Now, we use different power quality terminologies to characterize or to classify these different voltage or current quality problems. Okay. Those terms are like transient problems, short duration voltage variations, long duration voltage variation, voltage imbalance or unbalance, waveform distortion, voltage fluctuations and power frequency variation. So, these are the different power quality terminologies which are used to classify different voltage or power quality aspects or power quality issues. Okay. So, this table gives you some different types of power quality problems and they are possible and the causes of encountering those power quality problems in power distribution networks. And also this table will give you some how do we characterize those power quality problems. Okay. So, the category 1 is transient type of power quality problem and there are two types of transients. One is called impulsive transient, another is called oscillatory transients. Okay. Now, what are those kind of transients? I will discuss a little while after, but you need to know at this point that how do we characterize those transient power quality problems. Basically, for impulsive type of transient we classify them, we characterize them on based upon this peak voltage magnitude and rise time and duration. Okay. And the possible or typical causes for this impulsive transients are lightning strike. Lightning is one of the reason for having this type of power quality problems. Transformer energization and capacitor energization or capacitor switching is created another sort of transient. Okay. Similarly, this oscillatory type of transient we also characterize them based upon this peak magnitude and frequency component. So, there is a difference between these two types of transients which I am going to discuss in one of my slides. Okay. And possible reason for this possible causes for this oscillatory transients are line or capacitor or load switching. Okay. Now, next category of power quality problems are short duration voltage variation. Okay. Short duration voltage variation. So, for this short duration voltage variation, the typical period of occurrence is very short, which lie within a few cycle up to 1 minute. Okay. From a half cycle to 1 cycle to up to 1 minute. Okay. So, if so this kind of problem sustains for a very short period of time, okay. But I will discuss the impact of those kind of short duration power quality problems, which are not even short duration. So, impact will be long duration problem. Okay. So, that is why their mitigation at the time of the occurrence is very important. Okay. So, those things we will discuss. So, voltage sag is sudden short duration voltage dip, okay, which is characterized by its magnitude and duration. And the possible causes for this kind of power quality problems are ferroresonant transformer, single line to ground faults, which are very frequent types of faults the distribution networks they encounter. Okay. So, single line to ground fault is very frequent fault for distribution networks, okay, which may cause voltage sag. Okay. And this voltage sag is characterized by dip in the voltage magnitude and the duration. Okay. Similarly, voltage swell is just opposite of the voltage sag, it is basically a short duration rise of voltage, which is also characterized by voltage magnitude and the duration. And it occurs due to the same reason as the voltage sag, that is ferroresonant transformer and single line to ground fault. Specifically, single line to ground fault, as I said, it is very common in power distribution network. Also, we have a short duration voltage quality problem, that is called short duration interruption. Okay. So, it is characterized by the duration. Interruption means, I will discuss, the interruption means sudden, if the supply voltage becomes 0 per unit suddenly for a very short period of time, less than 1 minute. Okay. So, this occurs due to some temporary or transient type of fault, which are self clearing. Okay. As I said, in distribution networks, they are encounter many faults due to non-technical reasons. Okay. And one of the reason is that weather related or this animal related issues. So, if at any instant of time any branch of a tree which is located near to the distribution line is suddenly touched, suddenly gets touched with this one of the phases of the distribution line, which may cause a transient type of fault within a few second or within a microsecond of time they get detached, and thereby they create a transient fault which is self clearing. Okay. And this may sometimes cause voltage sag, voltage swell in other phases and also cause voltage interruption. Okay. But although they are short duration voltage variation, they last for a few cycle up to 1 minute, but their impact is not much, impact is very heavy. So, those things we will discuss, and we have different mitigation approaches because of that, those things we will discuss. Similarly, we have a long duration voltage quality problems which include under voltage, over voltage and sustained interruption. Okay. So, under voltage is similar to voltage sag, it is a dip of the voltage which occurs for a period of time which more than 1 minute. Okay. So, they are this is also characterized by magnitude and duration, and the reason is switching on this load, capacitor de-energization etcetera. Similarly, over voltage is a sudden rise in voltage, and if it sustains for more than 1 minute, it is categorized as over voltage. It is also characterized by magnitude and duration of this magnitude of the over voltage and duration of this over voltage, and it occurs due to switching of a very large load, and so. Similarly, sustained interruption when supply voltage becomes 0 for more than 1 minute, it is categorized as sustained interruption, and it occurs due to faults as we know. Okay. Similarly, voltage imbalance, it is another important power quality problems. What do you mean by voltage imbalance? Imbalance means since you know that our system is a 3 phase system, and balanced 3 phase system refers to a system having same voltage or identical phase voltage of all the 3 phases, as well as these voltages are exactly same spaced in the phasor. That means, they are 120 degree apart to each other. So, if anything, if it deviates any parameter, meaning that if any of the phases voltage is much higher or lower than the other 2 phases, then it will cause a voltage unbalance. Similarly, even though we have same voltage magnitudes, but they are if they are spaced anything not 120 degree apart to each other, then it will also cause voltage imbalance. I will discuss this, and it is characterized by a well known method called symmetrical component analysis, and the reasons of this voltage imbalance single phase loads, single phasing conditions, those things. Single phasing condition is another type of faults. Okay. Similarly, waveform distortion is another category of power quality problems. There are some subcategories which are called as harmonics. Harmonics means as I said, we will discuss in one of our slides. Harmonics are generated because of some non-linear loads, and these are characterized with a index called THD. THD is an index which is named as total harmonic distortion. So, it quantifies how many harmonic components we have, or how much harmonic components we have either in voltage or in current. Okay. Similarly, notching is another sort of waveform distortion. So, harmonic is basically a periodic type of waveform distortion, and notching is very short duration waveform distortion. Similarly, DC offset is another kind of waveform distortion. These are the way they characterized, and these are the reasons having this. Mostly this waveform distortions occur due to the presence of power electronic devices or power electronic converters, or in fact, many of the devices in industry or domestic applications we use power converters. So, they create harmonics, they create waveform distortion. I will come to that. Similarly, voltage flicker is also sudden change of your of the supply voltage, which causes sensation in our eyes. So, this is called as voltage flicker. If there is a arc furnace type of load or arc lamps used in some locality. So, this will cause this kind of voltage or power quality disturbance nearby the locality. Okay. So, they are this is characterized by frequency of occurrence and modulated. Okay. Now, in order to guide the electric utility, also in order to properly plan for the mitigation of these power quality issues, there are some standards which are developed primarily by IEEE. You know, it is an world famous body for electrical and electronics engineers, which is full form is Institute of Electrical and Electronics Engineers. Another is IEC, which is International Electrotechnical Commissions. So, they had some task force to develop or to make these standards, so that these power system planners or even power system customers, they will get to know that how much power quality problems are acceptable, and from which point these power quality problems will start unacceptable. For example, as I said, harmonics we categorize we characterize it with a index called total harmonic distortion or THD. Now, how much THD will be acceptable in our supply voltage, and also how much is from which point it is not acceptable. So, those things you will get from the standards. Okay. So, classification of power quality, transients, voltage swells, harmonics, voltage flickers, they have different standards. So, if you go through this standard, you will get to know that how much distortion is or how much harmonics are acceptable and how much are not. Okay. Now, let me discuss these power quality problems one by one. Okay. So, we will start with transients. So, transient type of power quality problem is a short duration problem due to sudden change of state. Okay. And as I said, transient types of power quality problems can be categorized as impulsive transient and oscillatory transients. Okay. And impulsive means you know, it is type of transient which is associated with certain impulse. So, as you know, impulse means is a sudden non power frequency change in the supply voltage. Okay. And it is most importantly, it is unipolar in nature. I will show you in my next slide how it looks like in a how it creates a waveform distortion. Okay. So, these transients they call they although they are very short period of time, but they causes this waveform distortion. Okay. I will show you. And it is a this impulsive transient, it is categorized with a rise time and decaying time. Similarly, oscillatory transients unlike this impulsive transients which are unipolar in nature, the oscillatory transients are bipolar in nature. Okay. So, it gives a sinusoidal component that get multiplied with decaying term. So, they are characterized with some e to the power decaying term lambda t multiplied by some sin omega t plus minus phi. Okay. So, they are characterized by some decaying term along with the actual sinusoidal quantity. Okay. Now, this is the example of you know that voltage impulse. You can see the impulse means sudden increase in voltage, which is of higher magnitude, where the nominal you know peak value of the voltage is 1 per unit. For a very short duration of time, impulsive voltage magnitude may go as high as 6 to 8 per unit, that is 6 to 8 times of the nominal peak voltage, which is pretty high, but it lasts for very short period of time all in terms of microsecond or nanosecond. Okay. So, these examples you will get voltage and current impulsive transients. Okay. Similarly, this is the example of oscillatory transients, which causes some decay in term. So, they last for some period of time, then after that they go for steady state value. Okay. So, here it is voltage magnitude per unit is given, it is not this voltage waveform as such. So, it have a oscillatory transient first few cycle of very high magnitude, but not as high as the impulse transients, but they are have they may be of twice of the nominal peak value of the supply voltage, but they take some considerable amount of time, which is in the range of millisecond and so to die down. Okay. Now, we will come to short duration voltage quality problem or short duration voltage variation. As I said, this short duration stands for few cycle up to a half cycle to 1 minute. So, if there is a voltage quality problems which last maximum for 1 minute, we will categorize it as short duration voltage variation. Okay. So, this occurs due to faults, single line to ground fault is most common cause for this type of voltage quality problems or voltage variations, and they are having some significant impact. Okay. And also energization of large load and intermittent loose connection in the wiring. Okay. Now, there are three types of voltage short duration voltage variation or short duration voltage quality problems. One is called voltage sag, one is called voltage swell, another is called interruption, short duration interruption. So, voltage sag is basically it is a fundamental frequency dip in supply voltage, fundamental frequency decrease in supply voltage, which last for some few cycle, even from half cycle to up to 1 minute. Similarly, voltage swell is it is an increase of fundamental frequency voltage magnitude, which also last up to 1 minute, from few cycle up to 1 minute. And interruption means when supply voltage becomes 0 or as less as 0.1 per unit, 0.1 per unit, that means 10% of the nominal voltage, for which last for less than 1 minute, called as short duration interruption. Okay. So, basically it is if I draw this problem voltage sag, it is something like that. Suppose this is your fundamental frequency voltage. So, suppose this frequency remains same, but it dips the magnitude for some few cycle like this, then it will cause this voltage sag. Similarly, so this is suppose voltage waveform with respect to time. Okay. Now, in voltage swell means your suppose this is your fundamental voltage, and for a certain cycle this voltage rises, okay, and it lasts for some few cycle, then it is called voltage swell. It is called voltage swell. So, this is voltage swell, this is voltage sag. And this interruption means suppose this is your fundamental frequency voltage and it becomes almost 0 for so a very short period of time, then it is kind of voltage interruption. So, this is V t, this is time. So, with this figure you can find out that how this voltage sag swell interruptions will look like if you trace out this voltage waveform. Okay. Similarly, this long duration voltage variations are their duration is more than of 1 minute. Okay. So, if the RMS value of the voltage reduced 10% or maybe 15-20%, it will call it under voltage, and if this RMS value rises to 10% or 15%, we will call it over voltage. Okay. And sustained interruption is again when supply voltage becomes 0 for more than 1 minute. It is similar to short duration interruption, but here duration is more than 1 minute. So, under voltage is basically increase of this RMS value of the supply voltage. It is the dip of the RMS value of the supply voltage, for more than 5 to 10%. Okay. 5 to 10% variation of voltage is acceptable. Similarly, over voltage is increase of this RMS value of the supply voltage for at least more than 1 minute of time or higher than 1 minute of time for a more than 10% of the increase of this 10% of the supply voltage. Similarly, voltage imbalance is another important aspect, or it is another type of voltage quality problems. It occurs when this individual phase supply voltage are not equal in magnitude and not equally spaced by each other. Okay. So, these are the two reasons. As we know that when we have a 3 phase supply voltage and if it is a balance. So, individual phase voltage magnitudes are same, as well as they are exactly displaced by 120 degree apart to each other. Okay. So, if does not satisfy that condition, then we call it as a case of voltage imbalance, okay, or voltage unbalance. And we will try to quantify this voltage unbalance, and we will try to restrict it for a given value of this number. Okay. So, what are the causes of this voltage imbalance or voltage unbalance? So, these are due to the single phase presence of the single phase loads in the 3 phase circuits, particularly secondary side of the distribution networks, where we have more domestic customers and they need a single phase supply. Okay. But electric utility generally they balance this loading of individual phases. But since different types of customers are connected in different phases, it is eventually not possible to have a identical loading in all the 3 phases. Okay. So, at that time this unbalance or imbalance will occur. Similarly, when we have a distribution lines with unequal line parameters, there is unequal voltage drop due to this unequal impedance of the line, and which are caused by unequal spacing of the phases, primarily due to this unequal spacing of the phases, then we may have this type of problem. In fact, this type of problems also occur in transmission networks, but we have different ways to mitigate this unequal line parameters, and that is called transposition. Okay. But in distribution lines they are not transposed at all. So, we have this kind of problems intact. Okay. Now, we have also this some voltage quality problems which are called waveform distortions. So, what are the different types of waveform distortions we have? As we said, one DC offset, that means presence of the DC voltage in the sinusoidal supply voltage is another reason for this waveform distortion. Also harmonics. Harmonics are basically they are periodic type of voltage distortion. Okay, I will come to that. And harmonics are generated because of UPS, adjustable speed drives, all are basically power electronics based loads, you can say, or power electronics based equipment, and they causes harmonic and they transmit harmonic to the system. Okay. If there is a harmonic present in the load, so this will be transmitted to the whole network as well, which will cause distortion in the supply voltage. Okay. So, similarly, notching is another periodic voltage distortion due to the operation of power electronics converters when current commutates from one phase to other. Okay. I will show you the typical type of this notching here. So, these are the notching. So, you can see they are very short duration type of waveform distortion. So, these are notching, and this is basically a distorted type of sinusoidal waveform. So, this is a distorted voltage waveform, and we know we can translate a distorted periodic voltage waveform into a number of sinusoidal voltage waveform by using Fourier series analysis, which will have some fundamental along with some many harmonics. So, this is a typical distorted periodic voltage waveform, which can be translated to a number of periodic waveforms, which are called harmonics. Okay. And IEEE they have some standards for a desirable harmonics, and this harmonics, as I said, we characterized with the index called THD, that is total harmonic distortion. I will come to that, how what is the mathematical function of this THD, I will come to that. But this THD is a measure, it is a numerically represent this amount of harmonics that we have present in a particular system, and these are the some limits of this acceptable THD. For example, when we have lower than 69 kV system, according to this standard voltage THD should be maximum 5% or lower than that, or acceptable voltage THD or voltage harmonics should be lower than 5%. Similarly, when we have a network with 69 kV to 161 kV, this THD should be 2.5% or lower. Similarly, above 161 this voltage to THD should be 1.5% or lower. Okay. Now, there is another type of power quality problem which is called voltage fluctuations, or we call this as a voltage flicker. It is a rapid change in the supply voltage which is called as voltage flicker, which cause some eye sensation, and this is basically caused by rapid variation in load current due to application of nonlinear loads. Okay. There is another kind of voltage quality problems or power quality problems, which is called power frequency variation. We intend to have a constant frequency, as I said, that is 50 hertz, but we never get it. So, there is some tolerable variation of supply frequency, often this varies from country to country, but anything plus minus 0.5 hertz is somewhat acceptable, and it also depends upon different factors. But if we have a frequency lie within this acceptable band, we do not have any problem. Okay. So far we discussed different types of power quality problems and what are the possible causes for those power quality problems. At this point, we will try and how do we characterize those problems, those things also we discuss. So, here at this point I will also discuss how do we mathematically represent those problems, so that we can develop some mitigation techniques or mitigation approaches for those problems. Okay. So, I will start with this analysis of unbalance, analysis of unbalance or voltage imbalance, which is somewhat taught in your undergraduate power system course. So, any unbalanced 3 phase voltage can be resolved into 3 sets of balanced phasors. One is called positive sequence, another is called negative sequence, another is called zero sequence. Okay. So, this is basically a concept which is given to us by Professor Charles Fortescue. Okay. In his landmark paper in 1918. Okay. So, he developed this concept that any unbalanced or any unbalanced 3 phase supply voltage or 3 phase supply current can be resolved into 3 balanced phasors. Okay. One is called positive sequence phasor. Here we will represent this all these phase voltages equal in magnitude, and they are displaced exactly 120 degree by each other, and they have same phase sequence as the original phasor. they have same phase sequence as the original phasor. Now, negative sequence, they are also represented by a set of equal magnitudes of these 3 phase vectors, and they are also displaced by 120 degree apart to each other, but they have some opposite phase sequence as the original phasor. Okay. So, positive sequence is one component of this this transformed value of this unbalanced 3 phase voltage. Negative sequence is another component, and another component is third component is called zero sequence, where we have 3 set of equal magnitudes of this voltage and they are exactly in same phase with each other. They are exactly same phase with each other. Okay. And this analysis is called symmetrical component analysis. This analysis is called symmetrical component analysis. Let me discuss a brief idea of Fatescu's symmetrical component analysis, so that you can understand in a better way. As I said, it is provided by Charles Fatescu in his landmark paper of 1918, almost 100 years ago, but still we learn it, we use it for many applications. We also develop this mitigation concept based upon this symmetrical analysis approach. Okay. Suppose we have a 3 phase system having unbalanced 3 phase voltages. Suppose this is phase voltage V A, this is phase voltage V B, and this is phase voltage V C. Okay. So, here you can see these V A magnitudes are not equal to V B and V C V B and also V C, and the angle they have, they are also not 120 degree, they are not equal to 120 degree each other. So, this will cause a unbalance or imbalance. So, this will cause a voltage unbalance. Now, this Fatescu says this type of 3 phase unbalanced voltage can be resolved into 3 components. Number 1 is positive sequence component, and this positive sequence components are represented by this suffix 1, that is V A 1. Okay. So, this 1 stands for this positive sequence component. So, 1 stands for positive sequence component, 2 stands for negative sequence component, and 0 stands for zero sequence component. So, this positive sequence components, in positive sequence components, all these phase voltages will be equal and they are exactly 120 degree apart to each other. So, this is V A 1, suppose this is V B 1 and this is V C 1. Okay. And they are exactly 120 degree apart to each other. So, this is also 120 degree, this is 120 degree, this is 120 degree, and magnitude wise also they are same, but they are also equal 120 degree apart to each other. So, this is a positive sequence. Okay. Now, let us see the how this negative sequence will look like. So, in negative sequence is here you can see this phase sequence of the supply voltage is same as that of the original phasor, that is here our phase sequence was A, B, C, because we assume that they are rotating anticlockwise. So, after this A phase B will come and then C will come. So, phase sequence is A B C. Here also you can see that phase sequence is of A B C. So, phase sequence is same as the original voltage. Now, in negative phase sequence, these voltage magnitudes they are equal and they are exactly 120 degree apart to each other, but their phase sequence is different. That means, they are rotating in opposite direction. So, negative phase sequence is represented by, suppose this is V A 2, here 2 stands for negative phase sequence. Then since the phase sequence is opposite, so here we will have V C 2 and here we will have V B 2. So, they are 120 degree apart to each other. So, this is 120 degree, this is also 120 degree, this is also 120 degree. Okay. And there is another component which is 0 sequence. In 0 sequence, all these 3 phase voltages, they are having equal magnitudes. Suppose this is V A naught or V A 0, then this is V B 0 and this is V C 0, then and also they are of same phase, they are in same phase. So, this is positive sequence, this is negative sequence, this is 0 sequence, sorry, this is 0 sequence. Now, actual this unbalanced 3 phase system is represented by summation of this positive sequence, negative sequence and 0 sequence phase voltage, and that is why this V A, which is actual phase voltage of this phase A is equal to V A 1 plus V B 1 plus V A 1 plus V A 2 plus V A naught. Similarly, V B is equal to V B 1 plus V B 2 plus V B naught. Similarly, V C is equal to V C 1 plus V C 2 plus V C naught. Okay. So, this is what this symmetrical component, many of you might be aware on this, and also this Fortescue gave a operator which is called operator A, or in some books it is also called as operator alpha, which is equal to 1 at an angle 120 degree, okay, which is 1 at an angle 120 degree. So, what would be the value of A square, which is equal to 1 at an angle, it is an unit vector. So, it will be 240 degree. So, which is also 1 at an angle minus 120 degree. Similarly, A cube, which will be 1 at an angle 360 degree, which is equal to 1, and also 1 plus A plus A square would be equal to 0, okay, would be equal to 0. Okay. So, by using this A operator, they determine they make a relationship of A 1 B 1, in fact B 1 and C 1 from A 1. For example, that here this V B 1 will be equal to A square V A 1, because it is minus 120 degree with respect to this V A 1, or it is 1 at an angle 240 degree with respect to V A 1. Similarly, V C 1 is equal to A V A 1. So, we can similarly replace this V 1 and C 1 in terms of V A 1, V A 2 and V A naught, which will basically give you a kind of matrix where we will get V A, V B, V C in one hand and some transformation matrix, and then we will be having this component V A 1, V A 2, V A naught. Okay. And this matrix is basically transform these components to this symmetrical component, and it is sometimes named as transformation matrix. So, this is how we will analyze, or how this is how we will characterize these symmetrical components. And in this part you will get to know that symmetrical component analysis. So, this is how we transform this. In fact, this is a reverse transformation. We represent this symmetrical component in terms of actual magnitudes of the voltage. Okay. So, similarly, current will also have similar kind of transformation, and here we have this transformation matrix represented by P. So, P is our transformation matrix. Transformation matrix, which transforms this ABC, that is actual phase voltage to 0 1 2 plane, which is basically 0 sequence, positive sequence and negative sequence or symmetrical component plane. Okay. So, now in fact, this here instead of finding out this transformation matrix, they find out this transformation matrix in different way, having a factor k, and this k value they are getting by making this power, that is expression of ABC plane equal to the power expression in 0 1 2, that is symmetrical component plane. Okay. So, this is how we can do it. Now, there are another way of characterize of this sort of voltage imbalance or voltage unbalance or even voltage distortion, which are called as instantaneous real and reactive power methods. These are basically used for developing the control approach for different kind of power quality mitigation techniques. So, which are very important, and those who will work on this control of this power quality problems or power quality mitigation problem, they need to learn it. What is instantaneous real power, what is instantaneous reactive power. So, here we get the definition of instantaneous real and reactive power. Since they are instantaneous quantity, they are represented by small v. Similarly, currents are also represented by small I. From this, instantaneous real power is defined as the dot product, which is very important to know. Dot product of this voltage and current vectors, which is shown over this equation. And instantaneous reactive power is defined as the cross product of this voltage and current, which is shown over here. Okay. And the scalar representation of instantaneous power is given by this. All these equations are very important to develop the control approach of this different kind of power quality mitigation techniques. So, these are vectoral representation of real and reactive power currents in terms of real and reactive power vectors. Okay. And also the scalar instantaneous apparent power is expression is this, and also we can represent this in terms of symmetrical component vectors like this. So, this is this you need to take a look if you are interested in further working on this. So, this is how this instantaneous active power is made similar to the instantaneous power in the 0 1 2 plane, that is 0 sequence, positive sequence and negative sequence plane. Now, we also go for different other analysis of distortions. As I said, here we are basically trying to understand how do we characterize this distortion. Okay. So, there are some periodic distortion and there are some non-periodic distortion. These periodic distortions are basically harmonics, in fact, notching as well, and also interharmonics. Okay. And their impact of these distortions, they will create increased loss, because I will show you that any distorted periodic waveform can be resolved into a number of sinusoid with different frequency, out of which fundamental frequency component is important for us, because that is what we are trying to provide to the customer as an electric utility. But what will happen to this non power frequency periodic distorted component, we call them as harmonic components. So, they will cause some extra losses, they will cause reduced equipment life, they will interface with protection and communication circuit, they will also interface with the customer equipment. And many times this customer, they generate harmonics and inject to the system. Okay. Now, these harmonics are, as I said, integer multiple of this fundamental frequency component, like n multiplied by f naught, where f naught is your fundamental frequency component, where n is an integer. And since we have a equal identical positive and negative half cycle, we do not have any even harmonics in power system, we mostly have odd harmonics. So, n is of odd number. So, we are concerned of some higher order even odd harmonics like third harmonics, fifth harmonics, seventh harmonics, 11th harmonics and up to that. So, those harmonics we need to study, and we need to have some mitigation approach for those harmonics. So, that the total harmonic contents will be lower, and we will get supply voltage as sinusoid as possible. Similarly, DC offset means n is equal to 0, interharmonics means n is non-integer, okay, any value in between 2 to 3 and so. And sharp harmonic is f is lower than your, this frequency is lower than the fundamental frequency. So, if your fundamental frequency is 50 hertz, the subharmonic frequency can be 25 hertz and so on. Now, we have some indices, as I said, to quantify this harmonic contents, and one of them is total harmonic distortion, that is THD. Okay. And THD is defined as the ratio of harmonic component to the fundamental component. So, here V 1 stands for fundamental component of this voltage, and this V n starts from 2 to any value is basically if you take root mean root square, then you will get this that harmonic or distorted component. Okay. So, we can always represent this RMS value in terms of this THD and the fundamental quantity, like here you can see this is equal to V RMS by V 1 square minus 1. So, we can always write V RMS is equal to V 1 multiplied by 1 plus THD square. So, this is also applicable for RMS value of voltage as well as current. So, this is suppose the voltage harmonics which is represented by THD V. Similarly, current harmonics we can write at I RMS is equal to I 1, where I 1 is the fundamental component of the current multiplied by 1 plus THD d I square. So, here this THD I represent the harmonics in the load current or line current. Okay. So, there is another index which is called distortion index. So, that this is same purpose, this is for the same purpose to quantify this distortion. So, that is called distortion index. Here numerator is same as that of THD, and the denominator is different. Instead of this fundamental voltage, it is basically RMS voltage, that is V RMS. So, this is this one is similar to V RMS. So, it is numerator is same as that of this THD, that is summation of n is equal to 2 to infinity. This is infinity in fact, this is also infinity in fact, this V n square divided by V RMS. So, the relationship of DIN and THD you can also find out, and this IEEE they prefer quantifying this harmonics by THD index, whereas IEC they prefer this DIN index. Okay. There is another concept here of this quantifying this power factor. This power factor, as you know, this real power or actual power or useful power consumed divided by V RMS I RMS, and if there is no distortion. So, this is coming out to be cos phi. Okay. But if there is a distortion, this distortion for distorted sinusoidal, this power factor is actually called as displacement factor, where displacement factor is equal to cosine phi, that is P 1 divided by V 1 multiplied by I 1. So, this is basically actual power, this is what the apparent power. And when we have this distortion in the currents, then the power factor is basically multiplication of distortion factor divided by 1 plus THD I. Similarly, if we have distorted distortion in the supply voltage, it will be also function of THD V as well. Okay. And actual power factor is lower than this displacement factor, that one should know. Now, these are the some of the ways we can categorize this voltage sag. In many people did research on characterizing this. One is called Detriot-Edison sag score, where simply the magnitudes of 3 are sum, or 3 phase voltage are sum divided by 3. So, if any of these voltage sagging in any of the phase, then magnitudes of any of the phase voltage would be lower than the nominal voltage. So, this core will be lesser than 1, and if there is no voltage sag, it will be equal to 1. Similarly, some people they consider this voltage sag energy to quantify this voltage sag, and people have used different indices to quantify this voltage sag. Now, mitigation approaches. So, these are basically power quality mitigation approaches, power quality mitigation approaches. So, this power quality mitigation approaches in power distribution systems are basically called, they are also obviously power electronic based controller, they are called custom power devices. Okay. They are called custom power devices. So, they are similar to fax devices which are used in power transmission system, but they are having a difference with these fax devices. Fax devices are normally constructed for relatively balanced transmission lines, whereas custom power devices they are constructed and controlled considering that relatively unbalanced power distribution networks. Okay. And these devices are used to provide following specification frequency to the rated power, magnitude and duration due to over voltage and under voltage. That means, if they use for over voltage under voltage mitigation, they used to have a frequency which will be similar to the supply frequency. They are used mitigate this harmonic distortion, voltage unbalance or voltage imbalance to mitigate voltage flicker. Okay. So, for this purpose we use them, and there are two types of custom power devices. One is called reconfiguration type, which are used to reconfigure this network. Okay, for current limiting, circuit breaking and current transforming devices. So, these are the some reconfiguration type custom power devices, which are called solid state current limiter, solid state circuit breaker, solid state transfer switches. And we have some power electronics based compensation devices specifically constructed to mitigate these power quality problems. They are named as distribution statcom or D-statcom. This is usually shunt connected devices and used for this mitigation for harmonics to provide reactive power compensation, and there are multifunctionalities. Similarly, there is a custom power device which is called dynamic voltage restorer. It is usually a series connected power electronic device, which is used to mitigate this voltage sag, voltage swell and many other power quality problems. And unified power quality conditioner, which is also called as UPQC, it is a combination of D-statcom and DVR. So, they have dual functionalities. They can mitigate current harmonics or load harmonics created in the customer premises. Also, they can mitigate this voltage quality problems like voltage sag swell mitigation and voltage flicker mitigation. Okay. So, for this part of the lecture, this is the main reference book that I took. In fact, this concept you will get in the Gonen book as well. Okay. So, finally, thank you for attending this part of this lecture. So, here we completed this module 3.